Hello, everyone. Thank you for joining us today. We are excited to present the final report for our project on AI-based sleep detection. We will discuss the problem we addressed, our approach, and the result we achieved. This project has been a collaborative effort by an amazing team. I'm Leonardo. I've worked alongside Rirena, Sean, and Khadija. The inspiration for this project came from the Sleep Timer app. The app allows users to set a timer and it automatically turns off music or videos that are playing to help users to fall asleep. However, the app has one limitation. Users might fall asleep before the timer ends or still be awake when it finishes. To solve this, the app needs a way to detect whether a user is asleep or not. Therefore, we aim to develop an AI-based sleep detection model using data like accelerometer readings, heart rate, and demographic information. The model will classify sleep into 6 stages to gain a detailed understanding of sleep patterns.
One of the challenges we encountered was class imbalance. So as we can see from the graph on the right, non-rapid eye movement stages 1 and 3 and rapid eye movement stage have much fewer samples compared to the others, which can bias the model towards over-predicting more common stages such as N2 and lead to poor classification performance for the underrepresented classes. To address this, we downsampled the data and took 15% of the training data set for each class to ensure that the model accurately classifies all stages. Another challenge was the distribution of the physiological data. We noticed similar patterns in the physiological signals across the sleep stages, as we can see from a screenshot of the mean values for the signals. There's a lack of sufficiently discriminative features. We saw that N1, N2, and W have a higher rate of misclassification, and this could be a contributing factor. Advanced feature engineering and spectral analysis can be used to extract the subtle differences between the signals.
In terms of actually setting up the modeling and sampling approaches, we considered 2 sampling approaches. So the first was concatenating the 2 million rows of data per participant for all the 100 participants to get a data set of 200 million rows. But obviously this was too computationally large. So what we did was we first class balanced and sampled down 15% of the data and then subsampled 100,000 rows from that for modeling. And essentially then created Boolean indicators for age, gender, and health conditions in order to capture participant characteristics and made sure that the participant ID column was not included in modeling to avoid leakage of information from training to test sets. The other approach we had considered was just considering X% of participants, like 80% in the training and then 20% in the testing, but this was still computationally intensive and would reduce participant diversity in the model in the training. And then after that, we considered a range of approaches, including ensemble methods and neural networks. And essentially, we found that the champion model was actually a random forest, which is like an ensemble of decision trees.
So to provide some context for our performance, the original data set without any modeling done, predicting only the majority class, which was the N2 state, yielded an accuracy of roughly 38%. So as shown in the chart, Random Forest emerged top performer with both an accuracy and F1 score of roughly 95%, showcasing its ability to balance both precision and recall. Now, LightGBM and our feed-forward neural network approaches did pretty well with just under 80%, showing solid performance. However, the other models fell short, really highlighting how a combination of sampling strategies and model selection that we chose to go with significantly increased our overall performance, proving Random Forest to be most effective in our case. Now looking at performance for Random Forest, here we have the confusion matrix represented as percentages, where each row is the true sleep stage and each column is the percent of predictions made for each stage. So our model demonstrated excellent classification for key stages, for instance, accurately predicting 98% of N3 and 99% of REM, showing real strength in recognizing deep sleep. Similarly, for preparation stage, it achieved pretty near perfect accuracy. However, some challenges do still remain. For example, 15% of N1 were misclassified as N2 and 6% as wake, reflecting difficulty in distinguishing between light and deeper sleep. So overall, our model's high precision in identifying deep sleep states is really impressive, but future enhancements should focus on refining classifications for the lighter stages, N1 and N2. And that is all we have for everyone. Thank you.
Thank you.